Alright, so in this video we're going to cover eigenvalues on a very basic level, and to go into that we have to talk about eigenvectors a little bit, but there will be another video dedicated to eigenvectors. So basically all eigenvalues is, for example, when we have any matrices and we multiply using matrices, that's a linear transformation on our plane. So let's say, for example, we have a vector on this plane that represents some movement this way. When we do that linear transformation, that is multiplying by a certain matrix, this vector it's going to change direction, most likely. Like, for example, it may go in the opposite direction and just be scaled so that it's bigger. But what eigenvectors are values that they're vectors that even after your linear transformation, they don't change direction. Sure, they might change the magnitude. Like, for example, here this vector was scaled out and it was bigger, the magnitude was bigger, but it didn't change direction. So that's your eigenvector. And so what this really is saying is that for your matrix A, there is a vector, which is your eigenvector, that's equal to the eigenvalue times that vector. That eigenvector the eigenvalue is that scalar. And so these two things are always going to be equal for this one particular vector and its corresponding eigenvalue. Because your eigenvector, because usually if for an n by n matrix, there's n eigenvectors and n eigenvalues, there's a corresponding eigenvalue for each eigenvector. So there's a particular, they pair up, they match up with each other. And yeah, so another thing I'm coming back and realizing I didn't mention is that what the eigenvalue is, what this value of k is just the value of how much this eigenvector is scaled. So if this vector is twice as big as this one, then the eigenvalue is going to be 2. So it's just how much it's scaled. So how are you going to find an eigenvalue then? Well, from this equation, we can say that we usually say AV equals, sometimes eigenvectors are written as lambda, so don't be thrown off if you see lambda v, and then we get that if you move this around, AV minus lambda v equals 0, and then A minus lambda I, which is just the identity matrix, because if we're subtracting, this is a scalar, it needs to be a matrix. Maybe I won't make it look like that. Times v equals 0. And our eigenvector, it can't be the 0 vector, it can't be the null vector, so this right here, A minus lambda I, has to equal 0, and that defines our characteristic polynomial of our matrix, which I'll get into in a second. And so I remember seeing this problem on Alchemist. And of course, this being AOPS Alchemist, it was like 2D matrix basics, where I don't think there's anything basic about eigenvalues. But here's a problem. So find all real numbers k for which there exists a non-zero two-dimensional vector v such that that matrix, which is A, v equals kv. So if you recognize the v is just your eigenvector and k is your eigenvalue. So basically all they're asking is when they say like find all real numbers k, this just means like, hey, find the eigenvalues. And I'll show you how to do that. So if we want to find the eigenvalues of this one matrix, what we're going to do is we're going to, for all the values on the main diagonal, we're going to subtract the value of the eigenvalue, which is sometimes, again, called lambda. So don't be thrown off if you see lambda. And we want to equate the determinant of this matrix to 0. So we're going to get 1 minus k times 1 minus k minus 16 equals 0. So you get 1 minus k squared equals 16. So 1 minus k either equals 4 or negative 4. And so that means that k either equals 5 or it equals -3. And so these would be our eigenvalues for this matrix, and they would both have corresponding eigenvectors, which is what we'll cover in the next video. But there is one more thing that I want to cover is, let me find an example problem. So this question, it's not letting me move here we go, that works. This question is from a mu alpha theta test. And, we could go through the entire process, put the eigenvalues on the main diagonal, solve for the determinant. But there's actually a much easier way to do this, because if you notice this polynomial, if you look at the characteristic polynomial of this, so if I were to expand this out, we'd get k squared minus 2k minus 16 equals 0. And so the sum of the roots here, which is -b over a, which is 2, that's the sum of the roots using Vietas, and that's also the sum of the eigenvalues, because your eigenvalues are the roots of your characteristic polynomial. So as you can see, the sum of them is 2, and that's what we get when we do Vietas. So if we want to find the sum of the eigenvalues, we actually can use this thing, knowing that the sum of the eigenvalues, because eigenvalues are roots of the characteristic polynomials, this is equal to the trace of the matrix. And so your trace is the sum of all the numbers on the main diagonal. So in this case, it would be 1 plus 4 plus 2. And that is equal to 7, and therefore the sum of your eigenvalues is going to be equal to 7. Okay, yeah, I just double checked with the solution key that the answer was actually 7 because it was an option, but yeah, the answer in this case was E, none of the above, and the correct answer was 7. So the trace is the sum of the roots, the sum of the eigenvalues, and another important thing you should know is that the determinant is the product of the eigenvalues, okay? It's the product of the roots and therefore the product of the eigenvalues, and that's the determinant. So product of eigenvalues, that's the determinant. Oh, which are your roots. That is the determinant. So those are some shortcuts that will save you a lot of time in tests. Alright, the next video will be about eigenvectors.